What happens when a helicopter's engine fails? Contrary to popular belief, it doesn't just fall out of the sky. In fact, the pilot is perfectly capable of landing safely with the remaining airspeed and altitude. This is made possible through the condition of flight known as autorotation. Autorotation occurs when an upwards flow of air drives the rotors rather than engine power. In order to understand autorotation, we will have to look at the upwards force acting on an aircraft known as lift.
Lift is determined by two main factors: the shape of the rotor blade, called the airfoil, and the angle of attack. This is the angle between the wing chord line and the direction of relative wind. Because the airfoil of rotor blades tends to be symmetric, helicopters typically rely more on the angle of attack to create lift. The more lift an airfoil produces, the more drag it creates as well. Drag is the force that opposes an airfoil's motion through the air. During normal flight in a helicopter, the engine spins the rotors, opposing drag and creating lift. When the engine fails, however, the pilot must keep the rotors spinning. To perform an autorotation, the pilot must skillfully manipulate three types of energy. These are potential, kinetic, and rotational energy. In this case, potential energy is the energy held by an object because of its position relative to other objects. Put simply, it is the position of the aircraft relative to the ground. Kinetic energy is the energy an object possesses due to its movement. In this case, kinetic energy is the helicopter's movement toward the ground. As the helicopter descends, the air beneath it pushes upward on the rotor blades and makes them spin. Now we have rotational energy. This can be observed in nature by watching seeds fall from maple trees. The distance from the seed to the ground, transferred into downward movement, creates rotational energy of these little seedlings so that they can glide to the surface. To understand how rotational energy creates lift, and therefore slows the rate of descent, let's take a closer look. During an autorotation, there are three regions of the rotor that are all doing different things. The inner 25% of the blade radius is called the stall region, where the angle of attack is too high for lift to be generated. From about 25% to 70% of the blade radius is the driving region. This is where that upward flow of air we discussed is translating into rotation of the blades. Finally, at 70 to 100% of the blade radius, we have the driven region. This region is being driven by the driving region and is also the region of the blades that is creating lift.
Now, imagine we're in a helicopter and the engine fails. Don't panic.
As your pilot in command, I'm going to reduce the angle of attack of the blades, which will then reduce drag on the rotors. The helicopter will begin to descend. It will be my job to manage the potential and kinetic energy of the aircraft in order to maintain rotational energy and control our descent rate. This will continue until about 40 feet above the ground, where I will put the aircraft into a flare configuration. This means we'll transition more of our downward movement into forward movement. Finally, I will use all of the remaining rotational energy transferred into a bit of lift for cushioning our touchdown.
Now, if you ever get the chance to really fly in a helicopter, you can be reassured with the knowledge that your pilot knows how to perform an autorotation.